Welcome AP students to Electrochem lesson 4. In this lesson, I'm going to go through a few different things that kind of interrelate cell potential to free energy, manipulation of concentration, and then we'll talk about cell potential and some formulas we can use to solve for your equilibrium constant. Okay, let's get started. So first, cell potential and free energy. We know that if cell potential is positive, that cell is spontaneous. The greater that positive value, fix that. The greater that positive cell potential, the more spontaneous it actually is. So the greater that spontaneity of the reaction is dictated by that cell potential or that E cell value, the voltage. This is also true of if you were able to calculate delta G. So delta G would actually be negative. The more negative it is, the more likely that it is spontaneous. The difference in those potentials of the anode and cathode, that EMF or that driving force, that electromagnetic force, is what we use to actually accomplish work or use as power or voltage, potential energy, to complete some task or to power some motor or whatever. So calculating free energy in terms of cell potential, the formula is down there on the bottom and it goes through what each of the variables are, but I'll talk just briefly about it. So delta G, K, and your cell potential, E naught, are measurements of that spontaneity, right? So if a K value is really high, greater than 1, it's going to favor the products and be likely spontaneous. If delta G is negative, it's spontaneous. And if the E cell number is positive, that means that it is also thermodynamically favorable. So we could do calculations of work, your cell potential times your charge, where Q is it's written down here. We're not really going to do much of this right here, but we will use it when we do electroplating and find out kind of how long it takes to plate certain metals. If that cell potential is positive, like I said, delta G would be negative. They'll be the opposite of each other. While I'm not going to derive the formula for you, it is given to you on your formula chart. I'm circling it down there on the bottom. Probably need to make that a little bit larger. But anyway, ooh, yeah, that's nice. So that's terrible. All right, so the delta G equals negative NFE. We call it the NFE equation, usually for short. But delta G is negative the number of moles, which is in Faraday's constant, which is 96,485 coulombs per mole of electrons. And then your E cell value, which is in voltage. And so you can use that to calculate what your delta G would be if you know your cell potential. And then the negative sign there, of course, will flip the sign of your cell potential, so your delta G would in fact be negative. Now, cell potential can also be manipulated by concentration. All the ones that are on your chart in your notes are standard cell potentials with 1 molar for both solutions. But if those concentrations are manipulated for some reason or they're not the same, it doesn't give you the standard reduction potential. It doesn't give you the same potential value. So in this case, on the bottom, it says, ask yourself, okay, self, based on the reaction below, what would happen to the cell potential if the concentration of the cerium-4 ion, which I'm circling, was doubled or quadrupled or increased even? If you increase the concentration of that ion, what do you think that would do to the voltage? Okay, well, if you increase a reactant concentration, would it not shift, just thinking of Le Chatelier's principle, to more products? The voltage is actually a product. And so if something gives off a positive voltage, then it is spontaneous. You would actually be making this more spontaneous by increasing the concentration of a reactant. That is also true in terms of the logarithmic function, which I'm going to show you, called the Nernst equation. Now, the Nernst equation as a whole is written down here on the bottom. There's a simplified one I'll show you here in a minute. This is not given to you on your formula chart, but it is useful in determining perhaps which way the reaction is shifting or what's going to happen to your cell potential as a result of manipulation of concentration. So it's derived from the same equation we had before, where delta G equals delta G naught plus RTLN Q, which is given up here. But instead of being in terms of delta G, using NFE plugged back in, we're getting the cell potential at these concentrations is equal to the standard cell potential minus RT divided by the number of moles of electrons times Faraday's constant, and then multiplied times the natural log of your products divided by your reactants from your balanced equation. And then all the stuff is listed down there on the bottom. Again, we're doing energy in this, calculating voltage, so we will use an R value that is in joules per mole K. The temperature has to be in Kelvin, and the rest is pretty self-explanatory. Another commonly used manipulation of the Nernst equation is down here on the bottom, because most of these reactions are done at 25 degrees Celsius. The 25 degrees C, Faraday's constant, and the natural log are all kind of combined into a single number, which now gives you log Q instead of natural log Q, and the number 0.0592 instead of all that other nonsense. This is the one that you'll most frequently use. If there is a manipulation in temperature, though, you have to use the previous, the full Nernst equation. That cell potential value that you calculate will be the maximum potential energy at the very beginning of that reaction, and that's important to understand. So this is the maximum potential energy at the beginning, because as the reaction progresses, the ions are going to be depleted, the electrodes are going to be coated, and so the battery is actually, or the galvanic cell is actually going to lose voltage over time, until of course its value is zero, and then the battery is said to be dead or at equilibrium. So, oh, I didn't mean for that to come straight up. I apologize. So calculate the EMF of a zinc copper cell at 25 degrees C under these following conditions. And so there is the battery or the galvanic cell listed there in line notation. And so it says, you know, you have a zinc anode, it's bathed in a 0.4 molar solution of its ions. We have a salt bridge as the double line, and then of course the copper 2 ions and copper metal. So if you were to write these things, it would be, and they tell you what the standard cell potential is, although you could go calculate it. It's important to actually look at the equation. So I've got the equation written down there, typed on the bottom. The reactant is Cu2 plus, and the product is the Zn2 plus. The other two are solids and will be left out of your equilibrium expression. If I go, and it says it's at 25 degrees C. So if I plug these values up into this equation up at the top, I'll have my cell potential is 1.10 volts. I'll then have, you know, the constant, the number of moles of electrons, which in this case is 2, because it's from a +2 to 0. 2 moles of electrons. And then I will log my Q value. Now my Q is, I don't know if it's at equilibrium, so I'm going to go find out. If I end up that my cell potential is 0, I will know that it's at equilibrium. It's likely not. But if I do products divided by reactants and I plug that in like this, okay, so I've got my cell potential minus 0.0592 divided by 2 times log of Q, which in this case is the product divided by the reactants, which would be 0.4 divided by 0.02. You're going to end up getting a value that is going to be less than your original cell potential. And I did. I got a cell potential that was 1.06. Now, this makes sense. If I look at this reaction right here, just in terms of Le Chatelier's principle, we have reactants, we have products divided by reactants. So I have this product value up here and this reactant value down here. That means I have a greater amount of products than I do reactants. So it's going to shift back to, or at least hinder the formation of that product, because you have more products than reactants. And so in Le Chatelier's principle, it makes sense. If I look at it in terms of logs, that number would be greater than 1. So that value would be positive. I would be subtracting that positive value. So yeah, my voltage is going to go down. So there's a lot of different ways that you could look at this. This would still be spontaneous as it's written, as these concentrations are present, because there is some of the ions present. It's still spontaneous, but it's not as spontaneous as it would be had they just been equal concentrations, or even 1 molar and 1 molar. So down here at the bottom, I hate that the answer just came up, but that's what we got. Therefore, the reaction is actually less thermodynamically favorable, like I stated. It is less spontaneous when you have a greater concentration of products than you do reactants. In the lab that we do next week, we'll actually manipulate some concentrations and see what that does as a result. And it is possible to simply have a cell of the same ion with different concentrations and produce a voltage. So a pH meter is, this was a question on a lab that we had a while back, is, you know, how does a pH meter work? But just reminding you, there are electrodes that are sensitive to concentration, and the pH meter is one of them. It has a concentration of hydrogen ions on the inside of the membrane, which is down here at the bottom. And there will be a concentration of hydrogen ions in the solution in which you're measuring. It compares those concentration of ions and figures out what that voltage is. So essentially, what a pH meter is doing is calculating using the Nernst equation to find out what that difference in potential is, and then solving for what that difference in hydrogen ion concentration is. And then it tells you, oh, well, the pH is this or pH is that. And so it's measuring hydrogen ions in that fashion, which is kind of cool, I think. It's a practical application of the Nernst equation. Cell potentials at equilibrium. Their cell potential at equilibrium is actually 0. So if I plugged into that simple equation for the simplified, I should say, equation for the Nernst equation at 25 degrees C, I would plug in 0 for what my cell potential would be at equilibrium. That doesn't change your standard cell potential. It's just whatever it is you calculate from the chart. But you could go solve for what your K value is. Now, a simplified version of this, or just getting rid of the 0, gives you this equation down here at the bottom. And if you can calculate what your standard cell potential is from the chart, you could then, and you knew the number of moles of electrons, you could then go solve for what your equilibrium constant is. So this is a lot like our Ratlink equation with delta G. We did our delta G equation, it was negative RT ln Q or ln K, and you could go solve for K if you knew your delta G value or you calculated it. Here, you could calculate your standard cell potential from a chart and then find out what the equilibrium system's constant would be. Just kind of nice, kind of cool. So here in this equation, this question, it says determine whether the following reaction is thermodynamically favorable. So we're finding out if it is spontaneous, and calculate the equilibrium constant at 25 degrees Celsius. Okay, so the 25 degrees C is relevant because we can use the equation we just went over right up here. We can use 0.0592 over n log K and solve for K. And I've gone ahead and plugged in and calculated what my cell potential is from the chart right down here. And it says the half reactions would be as follows. They're given. I have both of those cell potentials. I did have to flip the nickel, right? So that I would end up having, it's said as written, right? So the nickel is actually flipped from your reduction potential chart. And when you add these two together, you don't actually get a positive voltage. You get a negative voltage. And in getting a negative voltage, you should know that it's not thermodynamically favorable. In order for this reaction to occur as it is written, you'd have to input a minimum of 0.1, well, something greater than 0.11 volts. If I wanted to calculate what its cell potential is, or excuse me, what its equilibrium constant is, I would take that cell potential and plug into 0.0592 over n log K and solve. The number of electrons that are transferred in this particular case was 2. So I would plug that in for the n value. And then I could solve for K by raising 10 to the power of whatever that the constant number is on the left-hand side of the equation. I don't know if the answer should really be 2.4, 2 times 10 to the negative 4. I think it's actually more like 1.9 times 10 to the negative 4. It doesn't really matter much. But I think the 2 moles of electrons are actually an exact number. So I wouldn't use those to dictate my sig figs. I probably would use the 0.11. But nevertheless, that's a great way to solve for your equilibrium constant, having been given or having calculated your cell potential. So that kind of concludes this lesson. I know it was short and sweet. I'll see you guys in the next lesson, and in which we'll cover batteries and some electrochemical cell calculations and hydrolysis or electrolysis of water and so forth. So I'll see you in the next video.